Can everyone hear me now? All right, cool. So yeah, so I'm going to kind of continue this discussion that Mike started. I'm going to do it in a slightly different fashion, but I'm a fourth-year grad student, obviously working with Mike Cooper, and here are a few of my other collaborators down here. So we'll start loosely where Mike left off. And so this is a picture that we put together, I think fairly well represents satellite quenching at redshift 0. And as Mike said, we have kind of starvation on this high mass end, and then there's a turnover where the restoring force in satellite galaxies basically is unable to resist ramp pressure stripping. And that is unique to the Milky Way, or this characteristic mass is unique to Milky Way-like systems. And so this is kind of a nice way to try and constrain the physics by looking at the quenching time scale and how it varies as a function of stellar mass. Another way that we can look at this problem, or trying to address this problem, is to understand how these quenching time scales vary as a function of redshift. And so when we look at higher redshifts, this model, if it doesn't evolve, kind of runs into a conflict pretty quickly. And so specifically, if you just look at redshift 1, which is not very, we're not moving back that far, the age of the universe, which I'm showing here is this dotted red line, pretty quickly runs into the conflict with these starvation timescales, or these quenching timescales, at roughly the scale of Magellanic clouds. And so if quenching is occurring in these systems, or at this satellite stellar mass, then we expect significant evolution in the quenching timescale in this regime. And so this is kind of motivated observational project that I'm leading using the DEMOS camera at Keck. And I'm sorry. Okay, talk louder. Is that better? Oh, sorry. All right, cool. And where was I? Okay, yeah. So this is motivated roughly redshift 1 spectroscopic observations that I'm leading, and I think this mass scale in particular represents, I would say, one of the more interesting scales at which to study satellite quenching. And that's primarily because we expect dramatic evolution in the quenching time scale, specifically in this regime. And so I guess as an unfortunate kind of coincidence is this scale is also just below the deepest spectroscopic redshift surveys to date. And one of the better surveys specifically is the Deep 2, Deep 3 survey. And so what I'm showing here is the U-B color as a function of stellar mass at roughly redshift 1 for this survey. And it, you can see this kind of sharp trend right here where the data seems to cut off. And that's just a consequence of the selection effects in this survey. So what I'm interested in is this region of this parameter space specifically. We want to understand the quench fraction at roughly 10 to the 9.5 in stellar mass, and the deep survey basically doesn't detect any of these objects. And so in an effort to understand this, we're targeting low mass satellites around groups at roughly redshift 1. We specifically need accurate redshifts in order to assign cluster membership. And then once we have cluster membership, we also need a high sampling density so that we can try and understand our incompleteness. But once we have cluster membership, there's a plethora of data in most of these legacy fields, so we can then use this cluster membership to understand quenching as a function of environment. Just a quick overview, we're specifically targeting groups in the growth strip, and so what I'm showing here in the red stars and the orange circles, those are the group centers, the cluster centers, and the black dots are the deep 2 and deep 3 redshifts that we already have in hand. We're also doing a little bit of work in the Cosmos field this fall to kind of supplement our observations. But as this is ongoing work, some of the data we already have in hand, and so I've started to do a preliminary analysis of this data. And so what I've overplotted here with the yellow triangles are good, like confirmed redshifts for these additional observations. And what's encouraging is that we are starting to populate the low mass quenched regime, which we're starting to fill in this region of the parameter space that the Deep 2, Deep 3 survey, or where the Deep 2, Deep 3 survey was lacking, and what we require for our science. But this, in order to relate this to the work that we've done previously, we kind of need to bend this on stellar mass and try and understand how quenching evolves as a function of stellar mass. And so we first want to look at what the field population is, because the field population at slightly higher redshift is going to be our progenitor population for the quenched satellites at roughly redshift 0.8, because they fall in and then it takes a certain amount of time for them to quench. And so this is just a standard UVJ diagram for colored by satellite, or is colored by stellar mass, and for what I am adopting as the field population. And so from this, we can get the field quench fraction. And there's quite a few less, but these are confirmed member satellites of the groups that we have that we're targeting around redshift 1. And what you can see is that down to satellite stellar masses of roughly 10 to the 9.5, we are measuring a quench fraction. And so the fact that we're measuring a non-zero quench fraction, again, is suggestive that the quenching timescale is going to evolve pretty sharply at these redshifts. And so another way to look at this is to bend it on stellar mass. And so here's the quench fraction as a function of stellar mass. The preliminary points that I've pulled together are here in magenta. We can compare these to literature data. And so the cyan are from the G-class survey, and the yellow is from the Geek 2 survey. And the field quench population is right here in the black. And so the fact that we see this noticeable offset from the field population is, again, just evidence that environmental quenching is happening in these scales. But when we look at the satellite quench fraction, we're not just looking at the environmental effects. Some fraction of those galaxies quenched in the field and were subsequently accreted. And so when we're trying to understand the physical mechanisms that are responsible for environmental quenching, we need to kind of remove the fraction of galaxies that quenched in the field and were accreted. And so the way we do this is very simply to take the measured satellite quench fraction, subtract off the field quench fraction, and then divide by the star forming fraction. So it's a way of looking at how efficient is quenching acting on the star forming systems. And when we do that, we get this. So this is the quenching efficiency as a function of stellar mass. And when I first saw this, especially with regard to Stacy's talk yesterday, I was actually kind of encouraged. So we see a non-uniform quenching efficiency as a function of stellar mass. And this trend is actually seems to be very consistent with the quenching, with the trends that were required in Stacy's data to reproduce the star formation, or sorry, the mass functions in these environmental regions in the Z-Forge data. And so this non-uniform quenching efficiency seems to be apparent in our data as well. Ultimately, to connect this to physical mechanisms, we need to connect these to quenching timescales. And again, we do this through comparison to n-body simulations. And for this, I've used Bolshoi simulation and compared the accretion histories of satellite galaxies around clusters at redshift 1 to these quenching efficiencies, and we have a quenching timescale that looks roughly like this. And so this is all work that is in prep and ongoing, but ultimately we'll take these quenching timescales and try and understand how they vary as a function of both stellar mass and redshift in order to hopefully constrain the physical mechanisms responsible for these trends. So, thank you. For our field sample is well outside multiple virial radii. We actually do a very conservative cut on the field sample, and the models that we're building by somewhat arbitrarily having our mechanisms turn on at the virial radius, for the most part, that'll extend our quenching timescales, because since all of our timescales are built as the effect is assumed to turn on at the virial radius. So if it turns on at 2 or 3 R-vir, you're going to have similar trends, but you're just going to be yeah, it's also unclear, though. I would argue it's unclear that the environmental mechanisms that are required and their relative effectiveness is going to be. It's unclear to me that the hot gas halo, for example, is going to be built up enough at these epochs to affect galaxies out at 3 R-vir. Because in these systems, that's going to be close to a megaparsec. The host halos here are 10 to the 13.5 and more massive. So. Right. Yeah. So if I understand your point, so yeah, these 10 to the 9 live in roughly 10 to the 11 halos, but our hosts are closer to 10 to the 13 and higher at this scale. Yeah, so we're not actually, these satellites are not, we're not looking at Milky Way-like galaxies at redshift 0.8. These are closer to groups and large groups.